I'd like to welcome everyone to class today. What we're going to do is finish up the lecture on fiber optic sensors that we started on Wednesday. We got about halfway through, so we'll finish that today. On Wednesday, we did a lot of background on fiber optics, and we also did an example of fiber optics from some of the work, some of the research that we're doing in my lab. And today, we're going to switch gears and we're going to talk about some of the cool things that are being done with fiber optics, some of the products that are out in the market, some of the applications, and then we're also going to talk about your lab assignment. One of the nice things about fiber optic sensors is they can be used almost to measure almost anything. You have things from pressure to temperature to basically anything you can imagine, and people are coming up with more and more all the time. Fibers are cheap, they communicate at an incredibly fast rate. The signal you get from them is very stable, very predictable, just a wonderful tool when you're designing a new sensor. So here is just a few examples: temperature, pressure, strain, voltage, current, liquid level, rotation, particle velocity, sound, and the list just goes on and on. And we'll talk about some specific sensors in the next slides. Now, the principle that a lot of these systems use are really interference type systems, and so we'll go through that in detail. So what you have is you have a fiber. That's the end of the fiber is shown in the black circle there. And you have a light wave that is going down the length of the fiber. And it may hit something on the other side and bounce back. It may go all the way through. And what happens is, how does that light wave change based on whatever that sensor is doing? And so here's some more detail here. So for example, you have a fixed reference a certain distance away from the detector, and then you move that fixed reference, that delta X that you see in green there. And what happens is your signal, you have a different phase. And so here you can see the signal, for example, is 180 degrees out of phase. It may be 170 degrees out of phase after the signal is moved, and we can then convert that into a distance. So kind of the standard process of creating calibration curves and then applying the change in phase to a distance. So it's pretty simple. Another type of fiber optic system is you have a reference arm and then you have a measurement arm. And so you split the light into two beams. So you have the laser, it shoots it down a fiber. The fiber is split into two, and then it recombines. And when it recombines, the two light signals will be, ideally, they'll be exactly the same, and then they go and you have two identical waves at the detector. Now, if you apply a strain to one of the legs, the measurement leg, what happens is you'll get a phase shift, and that phase shift can be measured and detected and calibrated into a strain measurement. So it's another very simple tool using fiber optics. So here is an example of a temperature sensor using fiber optics. So you have a fiber optic cable, and at the end of that cable, you put a bifringent crystal. And what this does is it actually polarizes the light. So the light comes down in one direction and gets polarized upon the return. And change in temperature will cause a change in that polarization. and then you measure the polarization, and that tells you the change in temperature. So what you have is you don't have all these moving parts. It's just a simple small device that can go anywhere, is relatively simple to use and maintain. Now this is a device for measuring pressure. So once again, you just got a simple optical fiber, and you put this this little fitting on the end, and it has a diaphragm, and that as the pressure changes, that diaphragm moves, and the movement of that diaphragm creates a change in path length for the light. So once again, we're measuring phase change based on the diaphragm moving with pressure change. Very simple. The only moving part is the diaphragm. It's very small. Can be put anywhere. Just a great little device. Now we're going to talk about a different type of fiber optic sensor. It's a fiber Bragg grating, and these can be like what you think of as traditional gratings with like ridges, or they can be grooves in a fiber. There's several different ways to do these, and we'll take a look at that now. So in this fiber Bragg strain sensor, what you have is you have a just basically they're just grooves in the fiber, and what you have is as the light travels down that path, the transmission of that light changes based on the spacing and size of those grooves. And so as you stretch the fiber or compress the fiber, the size and location of those grooves changes, and that will give you a change in signal. So here is an example. You've got the Bragg sensor with the grooves close together, and you get this very tight signal. You stretch it out, you apply strain, and the distance between the fiber Bragg grooves is expanded, and you get this longer wavelength signal. So, I mean, it's pretty obvious how it works, and it's simple, it's easy, and a lot of strain sensors now are this type of sensor versus the older strain gauge kind of sensors. This is just a better sensor. Now, we talked about the wavelength changing. I think this is not exactly how it works, but it's kind of an obvious example. Part of the light goes through the sensor, and part of the light gets reflected. And so I think in the top example there, you have let's say you have a white light source that has everything, and in its natural state, blue gets reflected, and you see the blue missing in the transmitted light. And then as you stretch that sensor, it changes to yellow, and as you continue to stretch that fiber optic sensor even farther, it moves into the red region. And what this is you're seeing certain wavelengths of light behaving differently based on that sensor. And so it's really both directions that you measure. So interesting how they work. And I think this is just a final way to look at it. You see this unstrained wavelength and how it changes to this newer wavelength when it's stretched. So I think we're just kind of going over a couple different ways here of how these work and trying to explain it and make it easy to understand. And I think this is the calibration curves a lot of these sensors work on. You have to calibrate the wavelength versus the strain, or the wavelength versus the temperature. Kind of basic instruments and measurements kind of methodology gets applied to these. And I just wanted to give you some scale, a way to reference these, that these instruments are tiny. If you look at the the edge of the pencil there, like all fiber optic systems, they're just minuscule, and that opens up really all different kinds of cool applications because they take up so little space that they're just much more efficient in that manner. You can put more into a system. For example, with strain, you can put more strain gauges to better understand than you can with traditional options, which is great technology, these fiber optic sensors. So now we're going to talk about some of these fiber Bragg grading applications. We kind of went over the theory, so now let's look at some ways they're used. So here's one of these fiber Bragg grading strain gauges. And the cool thing about them is these get embedded in materials. So these aren't applied to the surface, they're actually inside, and you're measuring strain, what's happening inside the product. You see them a lot in concrete. They put them in roads, they put them in all kinds of different concrete structures, bridges, and we'll see some more applications. So here is the Halifax Metro Center. Halifax, of course, it's snow, and more snow all the time. And so here's an application for these sensors. They're put in the roof. The loads get too big. They know, hey, we need to go out. We need to clean the roof and make sure we lessen the load so it doesn't collapse. Here's another cool application for these fiber Bragg grading strain sensors. This is the Sigma bridge, and it just runs the distance, and they're looking for strain problems and doing repair, doing maintenance, doing whatever work they need to do based on these strain readings. So really a bridge is an active thing. You think of a bridge as just this static thing that's always there. It is moving. People are monitoring them. People are looking at data to drive activity. So it's pretty cool. Now here's a wind farm. So you've got all these windmills creating electricity. You think of storms, you think of weather, you think of all the things that can happen if one of these blades comes off or breaks. I can imagine it being terrifying, one of these things flying through the air towards your farm or whatever. So these strain sensors are all over the blades. So it's another great application for them. Now this is an interesting application, the pressure on a hull for a submersible vehicle. And I know we just had last year in the news, one of these imploded on a trip to visit the Titanic, so you could see how important to understand stresses and strains in one of these. And this particular submersible has 7 fibers and has 97 sensors on those 7 fibers. So that's an example of how you can really pack the sensors into these systems. And really the purpose is to correlate FEA results in this particular test, was to correlate the FEA analysis with real-life submersion. And then you can use that to create models, to improve your models, to do more complex FEA because you have better boundary conditions, better actual conditions. So it's a tool to improve design in this particular application. Now, next time you get on a plane, you're going to experience these sensors in action. They run all through the wings. This is a composite wing on an A380, and you have sensors all over the wing to make sure that they understand the the strain that is happening on flights, and it'll trigger maintenance once again. If you start to see readings outside of specification. So here's an incredibly important application: liquefied natural gas containers. So we ship liquefied natural gas all over the globe in these big ships. They're designed specifically for this. You've got to keep them in high pressure, and you got to really control the temperature on these. Last thing you want is one of these ships blowing up in a port and destroying the whole town. And so these are incredibly sensitive temperature gauges in this particular application, where they're plus or minus a quarter of a degree over hours, just to make sure everything is running perfect. Okay, so let's talk about your lab you're going to be doing this week. And the first experiment is going to be a demo of one of these fiber brag grading systems. Now the second experiment is going to be doing some measuring the attenuation of one of these systems, so that you can see how the phase changes as the system changes. So this is what the experiment is going to look like: a signal generator. You've got some control electronics. You've got your oscilloscope. You're going to measure how things change, so it's a pretty basic setup. And so what you're going to do is you're going to have this input signal, and you're going to measure the output signal. And what you're going to do is change the length of fibers, and you're going to see how that signal changes. And that's the attenuation that we're looking at. So here's the experiment. We're going to start with a 1 meter fiber, and we're going to look at the signal in, we're going to look at the signal out, we're going to convert that to dB. And remember, when we do this dB per meter math, we're actually going to be looking at the result's going to be a negative number, so don't be surprised if it comes out negative. And what you're going to do is you're going to plot the dB loss versus length, and the slope of that is dB loss per meter. And we actually looked at this in the last lecture. One of the slides I put up, we measured this dB loss versus length. It's actually an important thing in fiber optics. It's basically how long can your sensor be in your system, and you can see that would be important if it was a wing or something or a bridge. So it's an important parameter in design of these fiber optic systems. Now we're also going to do some work with some different transmitters. We're going to use different LED wavelengths, and then we're going to look at attenuation versus those wavelengths. So that'll be an interesting little project, and this is really important. And we select different wavelengths of light to work with different fibers, to work with different sensor systems, to address these attenuation issues. So it's an interesting and relevant experiment. Then you're going to do another experiment around dispersion. We talked about that last class. So we talked about attenuation. Now we're going to talk about dispersion. And so we're going to measure the output signal for different signal frequencies. And here what we're looking at in this experiment here is you can see through this fiber. You have the light bouncing down the fiber, and it's surrounded by this cladding material. And depending upon the incident of that light, and it can come out at one length, and it travels a different length here, shorter. So this one has a longer path, and this wave has a shorter path. And what that really shows up is in this arrival time. And so we will look at this arrival and how it affects signal and signal quality. And so what you're doing is you're really looking at extinction, and what you're trying to figure out is extinction in this application. So you got this nice pretty square wave going in. It's a multi-mode fiber, so you get different light paths. And so what happens is your output signal is pretty degraded. And you're going to continue to change this until you see extinction, which is where you cannot see any more path, any output path. So it's an interesting project. In this final experiment you're going to do is some optical ranging. If you think of, I'm a golfer, so we use these optical devices to measure how far away the hole is from where we're at, or different applications like that. So that's what we're going to do here. And so here is one of these time of flight devices. This is what you're going to be using. Works on the velocity of light. It's fixed. We shine a beam. It gets reflected. We know the time of flight. We know the velocity of light. We can figure out the distance. Pretty simple, pretty straightforward. So this will be an easy part of the lab. Good luck, guys. I hope you have a great lab, and I'll see you on Wednesday.